Howdy, my fellow time travelers. Fractals are a universe of chaos. And this universe is built before our eyes with the repetition of complex forms. So, is it just ordered chaos? No, it's more than that. If you look around you right now, you're likely to see blocky, linear, and smooth if you are in a man-made environment, or branching, uneven, and irregular shapes if you are in a natural one. Why is there such a difference between the appearance of man-made and natural spaces? Why does one tend to look smooth while the other one looks rough? When trying to describe the natural, it comes down to one word: fractals. What are fractals? If you want to know about this fascinating universe, stay tuned until the end of this video because you may also win an imaginary island. Dead Bunny will bring the rest of this not so imaginary story to you today.
By definition, fractals are infinitely complex patterns that are self-similar across different scales. But do you know that there is a song where it's possible to find self-similar patterns? In Germany, a group of researchers found in a Michael McDonald song, Fractals. The team who was working at the Max Planck Institute for Dynamics and Self-Organization found self-similar patterns in the drum pattern of a recording of the 1980s hit song I Keep Forgettin'. This pop classic features drummer Jeff Porcaro, who was a member of Toto and has played for other big names like Steely Dan, Madonna, and Frank Sinatra. The signature rhythm in I Keep Forgettin' comes from Porcaro's handiwork on a pedal-operated cymbal known as a hi-hat. Porcaro fires off 4 hi-hats per beat for a total of nearly 1,000 notes by the end of the song. The study's authors analyzed the distinctive sound of a hi-hat in order to filter out all of the other instruments. Then they looked at 2 properties of the notes of the hi-hat: the spacing between hits and how loud each hit was. The researchers found that both the intervals and volumes could be described by a fractal pattern called 1/f noise. In this kind of noise, each octave carries the same amount of energy per unit of time. The description is sometimes referred to as pink noise because visible light, whose spectrum has this property, is a pink color. Fractals are tricky to define precisely. At the beginning of the 20th century, mathematicians Pierre Fatou and Gaston Julia discovered fractal patterns while looking at complex mathematical systems. Back then, these objects defied linear analysis. They were considered aberrations or scary mathematical monsters with infinite depth and complexity. They weren't very popular and were forgotten until the late mathematician Benoit Mandelbrot discovered them again while working at IBM Labs in Armonk, New York in 1980. There, he started studying strange repetitions in signal noise and later managed to develop an algorithm that modeled natural landforms using nothing more than a basic computerized typewriter. This is a huge part of Mandelbrot's genius, using rudimentary technology in ways no one had ever thought before in order to make huge discoveries about Earth. Who was Benoit Mandelbrot? He was a Polish-born French-American mathematician, born in Warsaw, Poland, November 20th, 1924. Universally known as the father of fractals. In Latin, the word fractus means broken or fractured, but Mandelbrot coined fractal geometry in 1975 in order to describe the mathematical phenomena he had encountered. The Mandelbrot set, the world's most famous fractal, is based on imaginary numbers. Kinda hilarious, right? What is it? Well, it's this. You've probably seen it before. Behind this image, there's a crazy mathematical formula that can make you cry the first time you see it. But in reality, the complexity of this set can be easy to understand if you divide this process into basic steps. So, every day we use numbers, and we're familiar with those numbers that help us in our daily lives. Now imagine a number that doesn't exist on that line with the other numbers. It's just imaginary. This number is I. What kind of number is this? Well, it's simply the square root of -1. It's just crazy to think about, and if it's just imaginary, how can it solve problems and create a journey through the incredible world of fractals? Well, it can. Despite the name imaginary, they are actually considered just as real as the real numbers, and are often the only way to describe aspects of the natural world. Now, if we plot real numbers and imaginary numbers on a 2D plane, we can finally visualize this crazy concept. Imaginary numbers are on the y-axis, and real numbers are on the x-axis, and if we pick any number in that space, we have complex numbers. Complex numbers are nothing more than the combination of real and imaginary numbers. At this point, complex numbers are just written as c and put in a nice function. The function of variable z equals z squared plus c. Why is this? First, because we love to complicate our lives, and second, because in this case, we can create the fascinating world of the Mandelbrot set. In fact, we can choose the value of z and find some point on our plane. So let's start this journey with this simple idea. If when plugging the result back into the function or iterating the number that we find grows to infinity, well, we can throw it in the ocean. But if the number stays small, we can keep it and create an island. Allow Disponi to explain.
At this point, the only rule that we need to follow starts with z equals 0. So if c equals 1, we can just say function of z equals 0 squared plus 1 equals 1. And this is our first number. Could be a very nice number for starting to build our island, right? Well, let's iterate. Too big for our nice little island. We found out that when c is 1, we get huge numbers, so we can throw them into the ocean. But what happens when c equals -1? Let's try iterating it. We'll find we have a really nice series of 0 and -1, and this is exactly what we are looking for. So -1 is part of the island, and most importantly, it's part of the Mandelbrot set. Now we get to visualize what kind of island we really have.
As you see the shape of this island materialize, you'll find it has an infinite border length. The area of our island is unknown. It can be estimated. It's about 1.506484 square units. Its actual size likely isn't a rational number. Anyway, isn't it amazing to have an imaginary island all to ourselves? So grab your beach towel and jump into the universe of fractals in nature. If you don't have one, you can find one in our store. There's a world in a grain of sand, and this is the world of fractals. There's a phenomenon called viscous fingering.
Not to be confused with vicious fingering.
This process starts when two fluids with different viscosities are mixed together. The more free-flowing fluid expands in finger-shaped intrusions into the other fluid. And according to nature.com, this has been observed in many different systems, including between fine grains, such as sand. A water cluster grows in an apparent fractal form when clusters are built up by water molecules. Fractals may revolutionize our understanding of the universe. Early cosmologists assumed that matter was spread uniformly across space. Astronomers agree with that assumption on small scales, but observations showed that this is not true. A dissident group of scientists claims that the structure of the universe is fractal at all scales. If this new theory proved to be correct, even the Big Bang model should be adapted. Some years ago, a new approach was proposed for the analysis of galactic clusters, and correlations were based on the concepts and methods of modern statistical physics. This led to the surprising result that galactic clustering is fractal and not homogeneous up to the limits of the available data. After further examination of data, the result is that galaxy structures are highly irregular and self-similar. The usual statistical methods, based on the assumption of homogeneity, are therefore inconsistent at all scales probed for now. Perhaps a conceptual framework based on fractals is necessary to identify the real physical properties of these structures. But at present, cosmologists need more data about the matter distribution of the universe to prove whether or not we are living in a fractal universe. Fractals are also found in trees, leaves, veggies, flowers, and more. Fractals can be used in telecommunication too. A fractal antenna uses a fractal shape to maximize the effective length and increasing the perimeter of a material in a given space. Such fractal antennas are also referred to as multi-level and space-filling curves, and their advantage lies in their repetition of a motif over two or more scale sizes, or iterations. For this reason, fractal antennas are very compact, multiband or wideband, and have useful applications in cell phones and microwave communications. Fractals have applications in medicine, biology, economics, computer science, and art. They can also be rendered in 3D. Another example is when they're used in software that create amazing images and animations of landscapes and clouds. So this is an incomplete list of examples. Now it's up to you to complete the list, so leave a comment now about your favorite fractals. Your opinion matters. And if you want to become a time traveler, don't forget to like, subscribe, and share for more stories told by an alien and her imaginary friend, a pair that otherwise can't be found anywhere. If you'd like to support us on Patreon, you can find a link in the description, as well as our store. In our store, you can get an exclusive Christmas-themed t-shirt, sticker, and mug. And of course, stay safe with a MyStoryYourStory mask.
If you like this video, please give it a thumbs up. If you don't, press thumbs down twice, just to be sure. Take it easy. Peace! Oh, by the way, I'm an alien. But not that kind of alien.
Hey. Right, sorry, that's
Universe.